In this video, we are going to learn how to make copper carbonate. And why would we learn this? Because if you mix copper carbonate with flash powder, it is rumored that you will get a nice green-blue flash. Some information about this: it's also known as cupric carbonate. Copper carbonate is insoluble in room temperature water. Heating it drives off carbon dioxide. You can see it's a CO3, so CO2 would be driven off. You're left with one oxygen, so it yields copper oxide. And again, it's used often in fireworks to produce a blue-green spark and or flame. It also occurs naturally in the mineral azurite, or also known as malachite. Copper carbonate is a little bit tricky to make sometimes, so I'm going to proceed with two reactions. The first one is using copper oxide, which we're going to actually make using air and metal copper, plus acetic acid will yield copper acetate. This is the reaction right here: 2CH3COOH aqueous plus CuO solid yields CuCH3COO2 plus H2O. So right here is our copper acetate. The second reaction is the copper acetate we just made plus sodium carbonate yields copper carbonate. And this reaction is as follows: CuCH3COO2 aqueous plus Na2CO3, which is sodium carbonate, yields 2NaCH3COO plus CuCO3, or copper carbonate. This is, of course, sodium acetate right here. The reason we need to start with copper oxide is because acetic acid will not interact directly with copper. We need to produce this first for the acetic acid to be able to work with it. Although our primary method to make the copper acetate will come from mixing copper with air and then with the acetic acid, there is another significant reaction which I will do if this is taking too long, because this reaction can be rather slow, and that is by taking hydrogen peroxide and adding it to the acetic acid, which produces peracetic acid or peracetic acid. The reaction for that is CH3COOH aqueous plus 2H2O2 aqueous yields CH3COOO, 3 oxygens, H plus H2O. Peracetic acid can directly interact with copper. It doesn't need copper oxide, and when it does that, it releases copper ions into the solution. These copper ions, though, are then free to work with acetic acid, which they do, producing more copper acetate, and that's what we're trying to produce up here too, is copper acetate. The reaction for that would be the free copper ions reacting directly with acetic acid, CH3COOH, yielding CuCH3COO2 aqueous. Now, as the copper ions are working with the peracetic acid, combining with it, it does break it back down into acetic acid, which is reacting with the copper, and the hydrogen peroxide. So it goes through a cycle here. The hydrogen peroxide then is broken down into water and oxygen. And I only plan on making the peracetic acid if this part of the reaction is going too slow. For our materials, we need copper metal around 4 to 5 grams, not very much. We need acetic acid, 30%. And I'm going to review mixing different concentrations of the same solution as to how I came up with that. We need a bubbler to produce air, to produce our copper oxide up here. We need hydrogen peroxide. I happen to have 18%. We need sodium carbonate for the last part of the reaction here, and that'll be around 30 grams. Of course, we need water, and we need a fabric mesh to hold the copper metal above the bubbler so that the air can actually get to the copper metal. I want to briefly go over the mixing different concentrations of the same solution I just mentioned. So what I'm hoping to get is a target of 250 milliliters of 30% acetic acid. Now, the variation in the acetic acid concentration that we're putting the copper into can be quite a bit. So you can go probably down to 10%, just above what vinegar would be, up to glacial, which is 100%. But and the higher the percentage, the faster this will react with the copper oxide we're producing. But 30% is a good value. Glacial acetic acid is pretty darn expensive, and so this is the value I came up with. 250 milliliters was just a good starting amount because that was the size of the beaker. We're starting with one solution of 12% acetic acid, and that's from some time ago. I have about 500 milliliters of that, and I have a solution of glacial. Now, I want to use mostly the 12% to get the 30%, then the glacial because of how expensive this is, and we're going to do that by using this equation: X equals concentration divided by volume times 100, which will give you the final percentage of mixing these two together. Because I want to use mostly the 12%, I have quite a bit of it, and it's much cheaper than using this. We need to find out how much acetic acid is in the 12% solution if I use, say, 200 milliliters of it, which I'm going to use. That way, to get the 250, I only need to use 50 milliliters of the glacial acetic acid. So to find out how much acetic acid is in the 12% solution, 200 milliliters of it times 0.12 yields 24 milliliters. So in the 200 milliliters, we have 24 milliliters of glacial acetic acid inside of that, but it's, of course, diluted because of the water it's mixed with it. And then, if, of course, glacial acetic acid is at 100%, so we multiply 50 mLs times 1, which is the 100%, and we get 50 mLs. So all of the 50 mLs of the glacial acetic acid is acetic acid. Now, to find out the total amount of acetic acid we take the 24 milliliters here and the 50 milliliters right here, and we have 74 milliliters in our final solution of actual acetic acid concentrated. Of course, again, diluted in the water. So to find out our final concentration here, we're going to go back to this equation right here and see if using 200 milliliters of the 12% and 50 milliliters of the 100% is going to work out okay for me. So again, that formula is X equals concentration divided by volume times 100. We know we have 74 milliliters. We've determined that right here of concentrated acetic acid, and we know we have a total of 250 milliliters right there. So we take that, multiply them together times 100. We end up with 0.296 times 100, which gives us a final percentage of 29.6%. So we do, in fact, have exactly what is needed for this reaction, which I chose, which is 250 milliliters of a 30% acetic acid solution. Even though some of my lines are crooked here, I hope that this explanation was of some benefit to you. Back to our methods here. Here's our 250 milliliter beaker. It has 30% acetic acid. This is the mesh I was talking about, the fabric mesh. The copper is at the bottom here, so that the air that comes out of the air pump here can come up, come down, and bubble through the copper, producing the copper oxide, which the acetic acid can work with. I'm going to do this method for about 8 to 10 days to see what happens here to the solution. However, at that point, if it doesn't seem to be turning a good blue-green color, I plan on adding hydrogen peroxide, as I mentioned, and the quantity is going to be difficult because it's hard to know how much copper acetate is already formed, how much free acetic acid is still there that the hydrogen peroxide can work with. So honestly, I don't know, a couple squirts, 10 milliliters, whatever, something in there just to produce some peracetic acid and push this whole reaction faster. Once this is complete and I'm satisfied that enough copper acetate is formed within the solution right here, we are going to add to it the sodium carbonate solution. Sodium carbonate dissolves in water at 20 degrees Celsius at around 0.26 grams per 1 milliliter water. So in 250 milliliters of water, you have approximately 65 grams that can dissolve in there, but I see no need to do that because I don't think I'm going to have that much copper acetate that's formed in here. So what I'm going to do is cut that basically in half, and I'm going to dissolve 30 grams of the sodium carbonate solution in 250 milliliters of water, which will then be poured in here. However, we have an acid here. We have acetic acid, and we're adding a base. So this is going to bubble a lot, etc. But as it does so, the copper carbonate is going to be formed and will fall out of solution because it's not soluble in water or either of these solutions really, and it will start to collect on the bottom here. And then the very next step is to filter this solution right here, collect the solid. We're going to save that and we'll dry it, and that will give us our final copper carbonate. Enough discussion and talking. Let's go do this. I had made this acetic acid solution here of 12% probably 2 years ago, and it's yellow just from sitting around, but it's still good. I'm sure it's been capped the whole time. So as we learned, we need to mix 200 milliliters of this with 50 milliliters of that to make our 30% acetic acid solution. Here's the 200 milliliters of 12% acetic acid, and of course on the right is the clear glacial acetic acid, 50 milliliters. So I'm just going to add this into here. Very straightforward. So we now have our 250 milliliters of 30% acetic acid. Transferring the 30% acetic acid solution to the beaker here. And then I'm simply going to put this mesh in here from a who knows, I don't know what, but you could probably even use the mesh that comes with, buying oranges or fruit sometimes. Maybe it won't be good. You need something fine to hold the copper. You don't want huge pieces in here because you want them to react as best as you can. So there's the mesh in there. And then here's my copper that I collected. And it's a mishmash of wires, a small piece of tubing there, So that's all you need, anything. And you're going to put this in there like so. Here's my relatively inexpensive aerator. I got it on Amazon for around 10 bucks. But it came with this tubing and an air stone, or a bubbler, which is awesome because it spreads the air out everywhere, the bubbles. You can see the copper down there just a little bit at the top of the air stone there. So as the air hits the copper, it's creating copper oxide, which the acetic acid can work with to create copper acetate. We're 36 hours out. The solution's cleared up quite a bit. The copper is still there, of course. It's slowly getting degraded. The copper acetate that's forming will stay in solution, so we won't expect any kind of precipitate until we add the sodium carbonate. It's day 5 now. I have had to add more acid to this beaker, acetic acid, because it was, of course, evaporating. The copper is breaking down slowly, but not nearly as quickly as I imagined it would. So I'm going to let this run as long as I need to. We'll just come back and look periodically. 6 days here, and I noticed there was something collecting on the bottom there. So I emptied this and wiped it up on a sponge, and it turns out, I can see it through a magnifying glass, that it's this stuff. It's breaking down in the acetic acid over time. So I'm going to take the stone off and put everything back together. Well, it's a lot louder, but we certainly couldn't have those contaminants in there. We know the copper is breaking down. We can see bits of wire there that are bouncing around in the solution, so that's a really good sign. We're at day 8 here. Things are going really well. Tiny bits of copper are floating everywhere, which is a great sign. And I am going to speed this up at this point a little bit by adding some hydrogen peroxide. We discussed that earlier, and I think it's time to do that, and then I'm just going to call it quits. Because there's an unknown amount of copper acetate in there, I'm going to just add some arbitrary amount of the hydrogen peroxide. This is 18% here. Not too much, just a little bit. We want some of the acetic acid always left behind to continue working while the peracetic acid is formed. Okay, keep watching. Here we are at day 9, and what a difference. That peracetic acid ate into the copper nicely, and there are copper ions everywhere. You can see how green it's become, and those will react with the what is extra acetic acid and forming even more copper acetate, which was the idea all along. So I'm going to let this run one more day, end at 10 days. I didn't expect that, but we'll stop then and go on to the next step. It's day 10, and it's time to stop this part of the process. At this point, I would have expected all of the copper ions to have mixed with the acetate so that most of what's in here would be copper acetate. Here's my sodium carbonate. The solubility of this in water, as we discussed, is about 1/4 gram per milliliter. So I'm going to use 250 milliliters here, which will equal the amount of the copper acetate that I have there. We're all set up here for the final step. I dissolved that 30 grams of sodium carbonate into 250 milliliters of water here. As I said, I transferred the 250 milliliters of the copper acetate solution to this 500 milliliter beaker. So essentially, we're just going to get this into here slowly. It's going to fizz and pop because it's an acid and a base, of course. And eventually, though, we should see our final copper carbonate fall out of solution. Instead of pouring it in, I'm going to do it in small amounts just so that we keep the bubbling, because we're mixing an acid and a base, to a minimum. At this point, you can start to see a slight color change, more turning of a green than a blue-green. Or I should say maybe a dull blue-green. I think we're right at the point where titrating it from an acidic solution to a basic solution here, which once all of the acetate is used up, we'll start to drop out of solution our copper acetate. I'm sorry, copper carbonate. And you can start to see that form right there even. I'm going to add just a little bit more here, and then we'll take a look at this from the side. You can see it form as I drip it in there. All that powder in there, those are bubbles. It's a copper carbonate. And you can see the precipitate that's formed in there rather quickly. It went from a clear blue to this kind of duller blue-green color. And I think we're done titrating. I'm going to mix this good, and then I'll start filtering it. Here's our solution of the copper carbonate. Nothing's changed since we just saw it, but I did want to take a piece of pH paper because we started out using a lot of acetic acid, and the solution was very acid. Copper carbonate's a base, and we can clearly see that this is a base. The calcium carbonate is so fine, I could not find a filter paper to filter it out of the solution. It went through every filter paper I had, so I let this sit overnight, and it's obviously nicely come to the bottom of this beaker. So what I'll do is decant what's off top here, and I need to get filter papers that will actually filter this out of whatever remaining solution there is. So I'll be decanting this into the 1 liter beaker I have on the left here best I can. I have no idea how much this precipitate will want to float about in here, so watch it carefully. So this arrived today. It's my 10 micrometer or micron filter paper. So let's go filter our copper carbonate. I'm going to start filtering the copper carbonate solution here. I did double filter paper this because I don't want to have to do it more than once. And I know this is going to be extremely slow. So what I'm going to do is come back periodically. I'm about a third of the way through filtering this. And yeah, it's been slow. But slow and steady will win this race. I'm about 3/4 done here. There's just a little bit left on the bottom, but the filter paper is practically full. This really would have been a good time to have vacuum filtration, which I don't have, but working with what I got. And I am going to wash this. There is some sodium acetate in here, so I'm going to run some distilled water through this, let that drip through, do it a few times, and then I'll have to switch to filter paper to get the rest of the copper carbonate out of there. While the distilled water continues to wash through here, that's about the 3rd time I've washed it, and I think I'm going to be done with that. I have some new filter paper here that's a little bigger. I'm going to save myself some tedious work, I think, but we'll run it through here. I doubled this also, and let's see if we can't just catch this last bit here and be done with the filtering. As this continues to drip through, it still needs to be washed, of course, with distilled water. I'm going to put that over here. This, on the other hand, has been washed many times. There's still a bit of water in there that's dripping through. When it's done, I'm going to lift this whole thing out and put it over here. Okay, it's not completely dry, but it's definitely far enough. It's pretty much stopped dripping. I'm going to open this up now over here. We basically have copper carbonate sludge here, but that should start absorbing the water pretty well. The second batch has now been washed 3 times also. So we're going to get rid of this, pull out the filter paper, and start drying it too. I allowed those filter papers to dry up a little bit, and then I scraped off the copper carbonate with this little device right here onto this new piece of filter paper. It's very, very fine. It's like putty or paint, actually. But copper carbonate and filter paper were transferred to this light bulb heater, and it will stay here until it dries. That sludgy copper carbonate that was on the other piece of filter paper dried enough so I could transfer it to a new piece here. And it's been heating for maybe an hour or so, but I think it's pretty dry. I'm going to turn this off here. There we go. And once all the water is gone, there's not a lot of it, but it is copper carbonate. This is a plain potassium nitrate flash powder, no copper carbonate. Okay, this is potassium nitrate flash powder and copper carbonate. This is a potassium permanganate based flash powder. This can be a little bit potent sometimes. Like that. This is a potassium permanganate based flash powder and copper carbonate. Maybe it didn't come across on camera, but there was definitely some green in that flash. And finally, we're going to look at those copper carbonate crystals under this microscope.